I actually welcome all of you to a very important part of the kinematics, that is three-dimensional kinematics of rigid bodies. Okay. So from now onwards, we'll be talking about the three-dimensional kinematics, which is very important for us, in the sense that it gives us the real picture of the mechanical systems, the mechanisms, the machines. Like we talk about gears, we talk about bearings, we talk about these turbines, we talk about the pumps. So their actual analysis, the velocity and acceleration analysis, is actually done in three-dimensional kinematics while we treat them as rigid bodies. So the formulas that we'll be using in three-dimensional kinematics will be the same formulas that we have discussed while we were talking about the three-dimensional kinematics of rigid bodies. Because the formulas that we have derived there are general formulas, okay? The formulas were general, like we had the formula for velocity of point P is equal to velocity of point Q plus angular velocity cross arc from P to Q. This was one of the expression that we have used. If you look at this velocity equation between 2 points of a rigid body, this velocity equation is a general equation. The velocity of point P can have three components along x, y, and z. Velocity of Q can have three components, okay? The radius vector from P to Q can have three components, okay, along x, y, and z. But what we have done, we have used this equation only for planar motion, okay, where we had the components of velocity were something vp along I cap, component of vp along I x-axis, component of vp along j-axis. We had equation of this type, okay. We were using these I and j caps. But now onwards, we'll be using these equations, and these equations will be used in the three-dimensional space, okay. They will be used in space. We will be having an additional component coming in. We'll be having the z component for all these coming. We'll be having the z component of velocity of point P, z component of velocity of point Q, as well as the z component of the radius vector from P to Q. The same change will be to the acceleration equation, whether we are talking about the velocity and acceleration equation in the ground frame of reference, or velocity or acceleration in rotating frames of reference, relative motion and relative velocity and relative acceleration. Whatever equations we have used till now, all the equations had the expressions along x and y coordinates. From now onwards, these expressions will be along three coordinates, okay, along x, y, and z. But before we go ahead in discussing the kinematics of rigid bodies in three dimensions, we have to discuss some important concepts first. So we have to discuss some important concepts. We should be acquainted with very important concepts before we go ahead in understanding or in applying the equations in three dimensions. So as far as our studies of the kinematics of rigid bodies in three dimensions is concerned, the studies will begin with the properties of angular velocity. We'll first of all talk about the properties of angular velocity. This is something important for us. Let's talk about first thing we need to know is about the properties of angular velocity. Okay, we should be knowing what properties of angular velocity are. The first and foremost property we will be talking about and we'll be discussing is called the derivative formula or the derivative problem. Okay, the derivative formula or the derivative property. The derivative property, or we call this as the derivative formula. This is very important, very important formula while we use the kinematics of rigid bodies in three dimensions. So what this formula talks about, what this formula is, as far as the formula is concerned, it's like, let's suppose we have a frame of reference, and let's call this frame of reference, this is a moving frame of reference. We represent this moving frame of reference by beta. And in addition to this moving frame of reference beta, let's suppose we have one more frame of reference, what we call as the ground frame of reference, and we represent this ground frame of reference by J symbol. Now, let's suppose we define a vector quantity. For example, there is some point in space, okay? There is some point P, and we draw a vector. Let's suppose this moving frame of reference, its origin lies at, say, for example, O prime. And with respect to this origin, we define our coordinate axis. Let's define this to be our x-axis. Let's define this to be our y-axis, and let's define this to be our z-axis. These are our three coordinate axes. This is x-axis, this is y-axis, and this is z-axis. Okay. And let's draw a vector. Let's define a vector, a position vector. Say for example, let's suppose we have a position vector drawn from point O to point P. And let's call this position vector by term Q. I represent this position vector by Q. There is a, actually we have been representing position vectors by the symbol R. Okay, but there is here we are representing it by symbol Q, because the vector that is defined in beta frame of reference needs not only to be the position vector, it can be the velocity vector, it can be the acceleration vector, it can be a force vector, it can be a momentum vector, okay, it can be an impulse vector, it can be anything, okay. It can be an angular acceleration vector. So we are representing it by a general symbol Q. Here I am just telling you for understanding purpose that let's suppose we are defining a vector, let that vector be a position vector, and we are representing this position vector in the beta frame of reference, okay, to a point P. And since this vector Q has three components, it will be having a component along x-axis, it will be having a component along y-axis, and it will be having a component along z-axis. So we can define, as far as our vector Q is concerned, we can say that our vector Q is having components, vector Q is having components along x-axis. We represent component of vector Q along x-axis. So I write this as qx I cap. It will be having a vector component along y cap. So I will write this as qy j cap. And definitely it will have a vector along z axis. I will write this as qz k cap. Okay, so that will be qz k cap. Its components along z axis. So these are the components of this vector along x, y, and z axis. While as this vector, I am repeatedly saying that this vector is defined in the frame of reference beta. I am representing this as a left superscript to this q, that this vector has been defined in the frame of reference beta, to make it clear that we are having one more frame of reference there, that is the J frame of reference, the ground frame of reference. Now this is also clear. It's also said to us that this vector Q can be differentiated in beta frame of reference. We can take the derivative of vector, we can take the derivative of Q vector, that is Q dot, and this derivative we can take in the beta frame of reference, because this vector is defined in which frame of reference? Beta frame of reference. I have been saying since the start of the kinematics that when we are taking the derivative of vector functions, like we take the derivative of radius vector, position vector, or velocity vector, or acceleration vector, or force vector, these derivatives are to be taken in the frame of reference in which the vector is defined itself. Okay, if you look at our vector Q, our vector Q is defined in beta frame of reference. So we have, if we have to differentiate, if there is a need of differentiating this vector Q is to be differentiated in beta frame of reference only, not in J frame of reference. That's very important. Okay. So you can obtain, like if you, this is the position vector of point P, we can say that this is the position vector of point P in beta frame of reference. If we have to calculate the acceleration, if we have to calculate the velocity of point P with respect to beta frame of reference, then we will differentiate the position vector with respect to the beta frame of reference. If we have to calculate the acceleration, then we will double differentiate the position vector defined in beta frame of reference with respect to the beta frame of reference. This is important. So we say that the derivative of this point P, this vector which is defined in the beta frame of reference, is being differentiated in the frame of reference in which it is defined. Okay, we call that as, this is vector Q, its derivative is written with as a dot at the top of it, and it's with respect beta. Okay, like this may be velocity vector, acceleration vector, or anything else. Okay. Now we also have one more information. We have the information that as far as this frame of reference beta is concerned, beta frame of reference is rotating with an angular velocity omega, and this angular velocity omega is with respect to the ground frame of reference. This is something very important. So it's like, for example, we have, let's suppose we have an aircraft. Okay, we have an aircraft. Let's suppose this aircraft is going along, we call this as an aircraft 1, it's going along, it's moving in this direction along y-axis. We have another aircraft, okay, we have another aircraft here, and this aircraft is also moving in the same direction. I call this as aircraft 2, it's also moving in the same direction. Okay, there is, say for example, a glider here. Okay, this glider is being observed, the motion of this glider is being observed by an observer in aircraft 2. So he draws a position vector. Okay, it draws a position vector. So this is a position vector. We write this as, this is the position vector drawn from frame of reference 2 to the glider. Okay, so if we ask the person, if we ask the observer in frame of reference 2, what is the position of the glider with respect to you, he says it is r2g vector. Okay, fine. If we ask him what is the velocity, he will say it is r2g vector dot. It is the differentiation of r2g vector. That will be velocity. If we ask him what is the acceleration, he will say it is r2g vector double dot. This is the acceleration, r2g vector double dot. This is the acceleration. This is the velocity. This is the acceleration. This is the position of the glider with respect to the aircraft 2. This information, this all information is provided to us by an observer in aircraft 2. Now let's suppose that this aircraft is rotating. Okay, this aircraft is undergoing some rotation. It's rotating like this. So an observer in the aircraft 2, with respect to the observer in the aircraft 2, we are at rest. Observer 2, the aircraft is at rest. The observer in aircraft 2 will never say that they are undergoing the rotation. Okay, but the observer in aircraft 1 will definitely tell us that this entire aircraft is undergoing rotation. And let's suppose observer 1 tells us that this aircraft 2 is having angular velocity omega. So this angular velocity omega is provided to us by an observer in some other frame of reference, which we call as a ground frame of reference. That is the case we have here. Okay, this is the case we are having here. We have the frame of reference beta, which is rotating with respect to the ground frame of reference. The information about the rotation of beta is being provided by an observer in the ground frame of reference, and the observer in the ground frame of reference says that it is rotating. So this information about the omega is provided by an observer on the ground. Now there is. So it's like, let me rewind the problem. We have two frames of reference, a ground frame of reference and a moving frame of reference, beta. J is the ground frame of reference. We are defining a vector with respect to beta frame of reference, and vector is q. We are taking the derivative of this vector q with respect to the beta frame of reference. The derivative formula says the derivative of the vector q, the derivative of the vector q with respect to the ground frame of reference. Where is the vector defined? The vector is defined in beta frame of reference. So its derivative is to be taken with respect to beta frame of reference. The derivative property or the derivative formula says that the derivative of the vector defined in beta with respect to the ground. Now, if you take the derivative of this vector q, not with respect to beta, but with respect to ground frame of reference, that is derivative of vector q with respect to ground frame of reference is equal to derivative of this vector is equal to the derivative of this vector with respect to the beta frame of reference. That is the derivative of this vector with respect to beta. We know q is defined in beta, so its derivative can easily be taken with respect to beta. But the derivative formula says the derivative of vector q defined in frame of reference beta with respect to the frame of reference j is equal to the derivative of this vector q with respect to beta itself plus angular velocity of this beta frame of reference with respect to ground frame of reference. That is angular velocity of beta with respect to ground frame of reference, and its cross product with the vector q defined in the beta frame of reference. This is called the derivative property or the derivative formula. Why this derivative formula is restricted is called the property of angular velocity. Why this is the property of the angular velocity? The reason for this is that if the two frames have zero angular velocity, that is, if this frame beta is not rotating with respect to the ground frame of reference, that is, if the value of this omega is equal to 0, when the value of this omega is equal to 0, then the value of the derivative in ground frame of reference is same as compared with as the value of the derivative of this vector in the beta frame of reference. These two derivatives become same. So we are defining a vector in beta frame of reference. And we are taking the derivative of this vector defined in beta frame of reference with respect to the ground frame of reference. Now the question is, what causes the change? Why is the derivative of a vector in one frame of reference in which it is defined different from the frame of reference, different from its derivative with respect to the ground frame of reference? The reason is this angular velocity. It is this angular velocity. So when one frame is rotating with respect to another frame of reference, the derivative of the vector in this rotating frame of reference will be different than the derivative of the same vector with respect to the ground frame of reference. These are important. And these two derivatives, these derivatives are restricted, are related to each other, not restricted. They are related to each other by a formula. The formula, we call this as the derivative formula. This formula is very, very important. The proof for this formula I will be giving to the students in the form of the PDFs that I have myself developed. They will be available to the students in their WhatsApp groups, the proof for the derivative, but I will not be discussing the derivation of this formula in the class, though I will be giving the notes for the derivation, how we have actually, derived this formula. The derivation will be given to the students, a very easy derivation. Students can follow my notes for that. But since I need to use this equation only, so I will only follow its what we call as and its formulation only, not its derivation. That's important. So this is one property. So this was the property one of the of the angular velocity. So we call this as the derivative formula. It relates the two derivatives. The second property is uniqueness of the angular velocity vector. The angular velocity vector is unique. So the second property which we will be discussing now is, so students need to remember this formula. The second property that we will be discussing now is what we call as the uniqueness of the angular velocity vector. That is the second property. As far as the second property is concerned, the uniqueness of the angular velocity is concerned, so our second property will be, property 2 is what we call as the uniqueness of the angular velocity vector. Uniqueness of the angular velocity vector. So this is the property 2. What is this uniqueness of the angular velocity vector? It says it's like this. Let me take the same. Let's say this is the frame of reference beta. This is frame of reference ground. And we are defining a vector q with respect to the frame of reference beta. Then we have the formula which we have just written, the derivative of vector q with respect to frame of reference ground is equal to the derivative of this vector with respect to the frame of reference beta plus angular velocity of angular velocity of beta with respect to ground frame of reference and its cross product with the vector q, which is defined in the frame of reference beta. Okay, this is. Now, if someone says that this angular velocity omega, the value of the angular velocity omega, it has the equation that satisfies the value of the omega that satisfies this equation. There are more than one values of omega that satisfy this equation. What does that mean? That means this equation gets satisfied at more than one values of the angular velocity of beta with respect to j. So we say, let's suppose one information that we have is, let's suppose the angular velocity of beta with respect to ground is, say for example, we call that as 1. Angular velocity of beta with respect to ground, we represent it by 1. This is one angular velocity of beta with respect to ground. Let's suppose there is some other value of the angular velocity that satisfies this equation. So we can write then this equation as angular velocity derivative of the vector with respect to ground frame of reference is equal to the derivative of the vector with respect to the beta frame of reference plus angular velocity of beta with respect to ground there is some other value of angular velocity which satisfies, we write that as 2 cross product with the vector q. Okay, let's subtract these two equations. As we are subtracting this from this, therefore this minus this is 0. So we write 0 is equal to this, and this will also cancel, they will be 0. So we are left with, we will write this as, this is angular velocity of beta with respect to ground 1 minus angular velocity of beta with respect to ground, but this is some other value of the angular velocities, because the argument is that there are more than one values of angular velocity that satisfies this equation. So we can write this as cross product with q. We are using the property of the cross product. So this is equal to 0. Since q cannot be equal to 0 because q is a well-defined vector in frame of reference beta, therefore we will write this term is equal to 0. That is angular velocity of beta with respect to ground, whose value we have taken there is 1, it's equal to angular velocity of beta with respect to ground, which we are saying there is some other value of angular velocity. But this equation says that angular velocity of beta with respect to ground is always same. That is what we write as angular velocity of beta with respect to ground. This equation says that beta cannot have more than one angular velocities with respect to the ground frame of reference. That is, there is only one value of angular velocity of beta with respect to ground. A ground observer will never tell us that the value of beta, angular velocity of beta with respect to me is omega 1 and omega 2. There are two angular velocities. No, angular velocity of a beta frame of reference with respect to the ground frame of reference is always unique. That's what we had already called the property 2, uniqueness of the angular velocity vector. That is, angular velocity of beta with respect to the ground frame of reference is always 1. That's always, it's always having a single value. What I mean to say, that 1, I mean to say it has a single value. Okay, it cannot have more than one values. Okay, this is called uniqueness of the angular velocity vector. This is the property 2. And the third important property that we have, very important property, that is called the additional theorem. Okay, the addition theorem of the angular velocity. So the property third, which we will be discussing, is what we call as the property third is the addition theorem. Third property is the addition theorem. The addition theorem. The addition theorem says it is like a very important thing. This is the last thing that we have to discuss. After that, we will take some problems using the already derived equation and solving the kinematics in 3 dimensions. So let's suppose we have a frame of reference, what we call represent by, we have a moving frame of reference, we represent it by beta. Okay. We have another frame of reference. We have, let me say, we have a frame of reference. Let me call this by C. And we have one more frame of reference here. That's what I call as beta. And we have a frame of reference, ground frame of reference. Let's call that as J. Okay. And let's suppose this frame of reference, C, is rotating with some angular velocity. It's having some angular velocity, and its angular velocity information is provided to us by a frame of reference beta. Observer in frame of reference beta says that the frame of reference C is rotating with angular velocity, omega. Therefore, what will be the angular velocity of frame of reference C with respect to an observer on the ground? Okay, the question is, we are having 3 frames of reference. We have frame of reference C, frame of reference beta, and frame of reference J. If the information provided is that the angular velocity of C with respect to beta is omega, okay, what is the angular velocity of this C with respect to the ground? The addition theorem says angular velocity of C with respect to ground frame of reference, angular velocity of C with respect to ground frame of reference is equal to angular velocity of C with respect to beta. It's equal to angular velocity of C with respect to beta plus angular velocity of beta with respect to ground, plus angular velocity of beta with respect to ground. This is called the addition theorem This is the third property of the angular velocity, though there are other properties of angular velocity as well. Like one of the property that we have, we will call that as inverse frame property, which we will discuss as we go ahead into the problems. But these terms are very important. These properties are very important for understanding the basic equations. Okay, so if we have the angular velocity of any body with respect to one frame of reference, what is its angular velocity with respect to another frame of reference? The relationship is angular velocity of C with respect to ground is equal to angular velocity of C with respect to beta plus angular velocity of beta with respect to ground. Angular velocity of beta with respect to ground. And we can easily prove it. The proof of this addition theorem is not too difficult. If we defines a vector in frame of reference C, okay, the proof of this is not that tough. Let me prove this theorem, the addition theorem I will be proving just now. But important is this much: these three properties we should be fully acquainted with. Let's have the proof of this addition theorem in the next class. Till then, thank you very much.